In this session, we're discussing something we all know is true. Security is getting harder. Threats scale, attackers adapt. Even when you do the right things, underlying assumptions in your apps or in the platform create risk. And AI is transforming how attackers operate and how we all must respond. In Windows, we're changing the model. But this isn't just Microsoft's problem, nor is it yours. We're in this together. We're raising the security baseline in Windows, so you can rely on stronger defaults and your customers stay safer out of the box. It's a shared responsibility that creates a safer environment for all. We remove insecure patterns from the platform. You build on modern, supported foundations. That's how we reduce risk across the entire ecosystem. Let's frame the journey. You'll see our shifts across 3 dimensions: reducing insecure legacy, enforcing code trust by default, and preparing for the next generation of cryptography. Let's start by removing some legacy code. NTLM creates real risk. We all know it. Many environments still depend on it. We're removing that risk while preserving real-world scenarios so you can move forward without breaking your customers. Start planning that transition now so your customers don't feel the impact later. Now, Mariam will walk you through how the platform is changing and what we're doing to minimize the impact on you and your users.
Thanks, Jeffrey. Like you mentioned, let's first look at what NTLM is and why it's considered weak and outdated. NTLM is an authentication protocol that goes all the way back to the early 2000s. It has since been deprecated, meaning it is no longer undergoing any active development, and organizations are strongly encouraged to move away from it and onto more secure protocols like Kerberos. Let's go through a typical NTLM authentication flow. In this scenario, a client is trying to access a resource. It connects to the server asks who you are, which is the challenge, and then the client provides a string with a username and password, plus the response to the challenge. The server gives access, and the authentication goes through. But what's the issue? Number one, there's no server-client verification, and so when the client is connecting to the server, it doesn't actually know that it is connecting to the intended server. So an attacker can intercept the request and act as the server. Problem number two, it uses super weak and old crypto. The message that the client sends back to the server uses an MD4-derived NT-hash and HMAC MD5 to compute the challenge response during authentication. And finally, problem number three, because of this lack of mutual authentication and the use of outdated crypto, an attacker can relay the challenge response to another server without cracking the password. So this, combined with the weak legacy hashing and the reusable NT hashes, this makes NTLM highly susceptible to relay and pass the hash attacks. Knowing this, you might wonder why NTLM is still prominent in so many environments. Some of the key scenarios where NTLM often becomes the only option for authentication are when there is no line of sight to a domain controller, in local account scenarios, or in scenarios where there is an unknown SPN or an IP address being used. So as part of our Windows security hardening mission, my team is fully committed to help organizations protect their environments against common attacks. And so to do so, we have prioritized the elimination of NTLM in Windows. However, given the several key scenarios where NTLM becomes the only option, we have dedicated our time to expanding Kerberos support in these exact scenarios. So first, we built IAKerb, which is an extension of Kerberos acting as a wrapper around Kerberos and enabling it in scenarios where the reach to a domain controller is restricted. We also built LocalKDC, which is designed to act as an authentication authority where it can talk to a SAM database on a given Windows instance and give out tickets for the identities that are local. So with IAKerb and LocalKDC, you can eliminate some of the most common uses of NTLM, further hardening the security of your organization and your environment. IAKerb and LocalKDC will be available in client and server WIP over the next few weeks, and you are going to be able to implement and test it. So now let's look at how IAKerb really works behind the scenes. In the first step, you see Kerberos authentication fails because there is no line of sight to the domain controller. The client then says, okay, I can still try IAKerb. So the client communicates with the server, both options for authentication, NTLM and Kerberos. The server acknowledges that it can use IAKerb and starts the negotiation process, first attempting IAKerb, and it succeeds. The client then gets the Kerberos tickets and succeeds with Kerberos authentication. One example where IAKerb applies is when there's a remote user working from home for a corporate that has public-facing corporate server, for example. And so to access the service, the user has to authenticate to the service, and for some reason, they have VPN issues. In this case, they cannot reach the domain controller, and the domain controller is behind a firewall, so they cannot even get a Kerberos ticket. So in this scenario, IAKerb acts as a proxy for Kerberos, and the server was essentially the middleman between the client and domain controller, as it forwarded the messages between them and enabled the client to get a ticket and present it to the service. And with that, authentication with IAKerb is successful. Now let's move on to LocalKDC, which is mostly used in workgroup or cluster scenarios. This works by having every Windows instance running a LocalKDC that interacts with the local SAM database on the given Windows system, and it has access to the local accounts. So when the client tries to authenticate the server will talk to the LocalKDC internally, and it will be able to mint tickets for this identity, enabling the authentication flow to go on. The security benefits here is that it replaces NTLM for local accounts, which is one of the largest scenarios where we see NTLM usage today. Now let's look at how authentication without NTLM and with IAKerb and LocalKDC goes in this demo.
Here, I'm going to try to access a file share in this standalone setup with two unjoined machines. First, let's block NTLM. Now, if we look into the Wireshark capture, we will be able to see what the client advertised to the server. In that advertisement, we're going to see that it advertised IAKerb. Now, let's see if we actually end up using NTLM. They exchange a couple of IAKerb messages, and eventually we get to a message that says, "Oh, everything was good. I was able to authenticate using IAKerb, and authentication succeeds."
Now let's move on into what we have already released, and it will take you a step further into enabling a more secure authentication protocol in your environment. Late last year, we released the enhanced NTLM auditing protocols, which went out to Server 2025 and Client 24H2. With the enhanced auditing, you will be able to know why NTLM is being used, where it is being used, and who the authentication request is going from and to. We highly suggest that you start using NTLM auditing today in your environment to know how NTLM is being used, and that will take you a step further into preparing into the overall disablement of NTLM in Windows. We are also excited to announce that over the next few weeks, we will also be releasing NTLM blocking policies. These blocking policies are available through the administrative templates under Systems and then NTLM. With these blocking policies, you will be able to selectively block specific scenarios of NTLM within your environment. So this includes SSO blocking, includes disabling NTLM for domain controllers, and so forth. This will take you one step further into starting to disable NTLM and looking at to see what breaks. With the enablement of IAKerb and LocalKDC, you'll be able to successfully move away from NTLM in your environment. And so what can you start doing now with all of these new features? One, start using the enhanced NTLM auditing feature, which we released last year. Again, this will tell you how NTLM is being used in your environment and what you can start doing today to mitigate those NTLM scenarios. Two, you start remediating, fix the unknown SPN scenarios, start registering your IPs, start to move away from third-party applications that are hard-coded to use NTLM. And then you can start in step 3, piloting IAKerb and LocalKDC in Windows Insiders for server and client. Those will be available in Server 2025 and Client 24H2 and above. So you can start enabling those features, and with the blocking policies, you will be able to see successful Kerberos authentication even when NTLM is blocked and in previously dependent cases. And then finally, you can even start to fully block NTLM in your environment, and you can always reach out to us at ntlm@microsoft.com to report any unique scenarios that you identify NTLM usages in, and we'll be happy to assist you in either migrating away from NTLM in those scenarios or putting them into our backlog of scenarios that we need to address moving forward. And that's it.
NTLM shows how we move forward together. We remove insecure paths, and we provide a working replacement. Next, we apply that same idea to code execution. Even with strong authentication, untrusted code can still reach users. So we're making trusted code the default experience on Windows. Geurten will show what that means and where we need you to adopt code signing for all of your code. including installers, uninstallers, scripts, and add-ons.
Thanks, Jeffrey. I'm Geurten, a TPM here on the Windows Platform Integrity team. Today, I'll be talking about new driver security and app control code integrity changes coming to Windows. These changes are all about eliminating common attack paths with built-in protection. This means fewer opportunities for attackers. Microsoft is tightening driver trust across the Windows platform. Cross-sign drivers are no longer trusted by default. We're moving to a model where WHCP certified drivers are becoming the baseline. You may ask why Microsoft is doing this. Well, the cross-sign driver program has posed a security risk for our partners and customers for years. This program had relaxed partner vetting and also didn't have anti-malware scanning, which meant malicious content was signed and abused. And the responsibility to protect signing keys fell to our partners, which meant keys were stolen in some cases. Additionally, the cross-signing program has been deprecated since 2011. Back in 2016, Windows already enforced WHCP signing for some driver scenarios, so we're simply expanding the enforcement. We're protecting compatibility for users and systems with a curated list of cross-sign drivers, which was informed by trillions of driver load diagnostic data signals. The feature rolls out in 2 phases. We start in audit mode, so Windows can measure impact to our users and the systems across 3 reboots and 100 system hours. We then move into enforcement, provided there is no impact to our users and the systems. The driver policy update is hitting Windows 11 24 H2 and newer platforms in the May 2026 security update. Windows Server 2025 is coming soon. If you ship drivers, the action is simple. Validate under audit mode and WHCP certify your cross-sign drivers now. Auditing your drivers is as easy as 3 steps. The first step is on a system with the May 2026 update or newer. First, check the state of the policy. Here, I've provided PowerShell commands to easily get that. Step 2 is to verify your drivers are WHCP certified using tooling like SignTool or SigCheck. If drivers are WHCP signed, they will be default trusted by the policy. Step 3. For non-WHCP certified drivers, you need to test them against the policy. PowerShell commands have been provided here. If you observe no event log entries, your drivers are trusted by policy. If you see event log entries, your drivers will be blocked by the new policy. The last step is for any non-WHCP signed drivers, regardless if they pass policy, we recommend going through the WHCP certification process. You could start by registering at the Harvard Dev Center, HDC for short. You need to then run and pass the HLK tests and submit the driver package to HDC, or Microsoft will WHCP sign your drivers. You want to finish by distributing the signed driver through Windows Update. Let's follow steps 1 through 3 to learn how to verify your drivers against this new driver policy. The first step is to determine the state of the policy. Here, I've written a script using CITool, which is an inbox utility, to get the policy state. In my system's case, the policy is in enforcement mode, so drivers will be blocked. The next step is to verify the signatures on each of my drivers. Here I have some Hello World drivers that I've written with various signature types to validate. To validate each signature, I'm going to use SignTool, which is a tool available in the SDK. With these parameters, SignTool will dump all the signatures on the driver, including any catalog signatures. We can see that my first driver is cross-signed. A cross-signed driver is any signature with a certificate chaining to a root that is not the Microsoft root. This driver may be blocked by policy, as cross-signed drivers are no longer trusted by default, except for an explicit list for compatibility scenarios. The second driver is WHCP certified. A WHCP certified will have a certificate that chains the Microsoft root CA 2010 in its signature. We can see that the leaf certificate is the Microsoft Windows Hardware Compatibility Publisher. This driver is default trusted by policy. I don't have to worry about it. The third driver is dual signed. It is cross-signed and WHCP certified. It is also default trusted by policy because it is WHCP signed, so I don't have to worry about this one as well. The last step is to test drivers against the policy. To verify my drivers, I'm going to load each one and evaluate any audit and block events. The only one that I'm worried about is the exclusively cross-signed driver, as it is no longer trusted by default. Here I have a script to automate loading my drivers and another to pull all the audit and block events for the Windows driver policy. You can see that the non-WHCP certified driver is blocked by the new policy. There is a 3076 event for the audit version of the policy, and also a 3077 block event for the enforcement mode of the policy. I will need to WHCP certify this driver, otherwise my customers will experience friction while using it. Switching gears to application security now. Application Control for Business, or simply App Control, is Microsoft's application control security feature for organizations. App Control is built directly into the Windows kernel on desktop and server, which prevents the need to install or download any clunky agents on top of systems. It can validate kernel processes like drivers, as well as applications and scripts, to lock down systems to run only trusted, authorized code. We integrate with Defender products to make reporting easier and to make reputation and intelligence-based decisions. Organizations all over the globe running Windows 10, 11, and Server 2016 or newer leverage App Control to secure their environments. Organizations with App Control face friction when your applications are unsigned, however. Help our collective customers by signing your code to make Windows more secure and reduce friction for our users. Smart App Control builds on top of App Control and shifts the Windows trust model from the Wild West and reactive AV blocks to a reputation and trust-based model. The feature is default enabled on Windows 11 on tens of millions of consumer devices, and the number of protected users is growing every day. Smart App Control trusts vetted content from the Microsoft Store, Windows components, and drivers from the WHCP certification program that we just talked about. It also trusts signed applications from CAs in the Microsoft Trusted Root program and content deemed safe by Microsoft AI Reputation Services. The feature does not trust unsigned apps without reputation, as Windows cannot tell who built it or verify the integrity on the content. It is critical to sign your code. If your code is unsigned and does not have reputation, this will result in friction for Windows users. Let's walk through how AI-driven app control stops malware. When a user downloads an app with good reputation from the internet, the app gets successfully installed and run on Smart App Control as is considered safe. When the user downloads an unsigned app without reputation, the user ignores any warnings and tries to install anyways. Smart App Control protects that user and the app is blocked from running. In the malicious case, the user unknowingly downloads a malicious application. Smart App Control determines that the code is malicious and the app is blocked, thereby protecting the user. As I've mentioned several times, unsigned code causes frictions for your customers. Your code must be signed to run smoothly now on Windows. Artifact signing removes every excuse for not signing. The Microsoft provided signing service is affordable, just $9.99 a month for the basic tier. The service is also fully managed by Microsoft. There are no added costs to you to manage certificates or keys, and you don't have to worry about key rotation or protecting key material. We do that for you. We've also met our developers where they are. We integrate in CI/CD pipelines like GitHub and ADO, and we also have CLI options. The service also uses digest signing, so your code does not leave your system. Only a hash of the content is sent to the service, so it is fast and secure. It is also part of the Trusted Root program, which builds reputation with Smart App Control. Finally, we recommend testing your code with Smart App Control enabled, which you can now manually enable in Windows 11 24H2 and 25H2. App Control also now supports a new framework to make your code app control aware. You just need 3 things to tailor your features based on the policy state. The first is an app control manifest. This can be on the system or remote. This file will describe the settings in your application. Second is the app setting definition. This is the name of the setting and its type. App Control supports Boolean or string types. The last step is calling the new Windows Lockdown Policy API, or WLDP for short. There is one API for each setting type. With these 3 pieces in place, your organization or users can write an app control policy which can control security behavior in your app. Let's take a look at how to do this. Here, I've created a secure plugin host with 2 secure settings. When app control policies are active and the secure settings are enabled, plugins must be signed, and the plugins cannot access the network. Let's see how to build something similar. We start with an application manifest. We start by defining the application ID, which is the name of the app in a setting. Each definition must have a setting name, a setting type, which can be a bool or string, and whether to ignore audit policies. The app manifest can be local on the system or remote, for instance on GitHub. Next, we call the WLDP get app settings APIs. We first import the WLDP DLL, and we use the API which maps the setting type, either the bool, string list, or string set API. For my app, I'm using the Boolean API. Next, we use the app manifest ID. This must match the ID in the manifest. We provide the name of the setting and the out result. This is the reconciliation app control does across all the policies. Finally, the API will return a status code, an H result. This can help you debug any issues. The status will be OK for successful calls. Let's take a look at how this works in practice. Here we have the secure plugin host running on a system. Right now, no policies are active, so the plugin host does not run in secure mode. The app control author specifies the path and location to the app manifest file for app control to consume. They also set the states of the settings they wish to enable or disable. The IT admin then deploys the policy, and on the next WLDP query, app control verifies the setting states and the reconciled state is returned back to the application. This is super exciting and impactful. You can see that your app now runs in maximum security mode based on how your customer configured their app control policy. Now back to you, Jeffrey.
What you just saw marks a shift in expectations. Windows is making a stronger promise to users. Trusted code runs with less friction. That benefits everyone, and it creates a clear responsibility. If your code isn't trusted by default, your users will feel that friction. Now, underneath all of this, cryptography forms the foundation. That foundation is changing just as rapidly due to the advent of quantum computing. Now, Jason will now take us through what we need to know about post-quantum cryptography and how you can stay ahead.
Thanks, Jeffrey. My name is Jason Fisher, the Group Engineering Manager for the Cryptography and Integrity team in Windows. As mentioned, authentication isn't the only thing that needs to evolve. Cryptography itself is facing a long-term shift. Thus, I am excited to be here today to talk about post-quantum cryptography in Windows. First off, what is a quantum computer? It's a type of computer that uses quantum mechanical phenomena, such as superposition, to perform operations on data. This allows quantum computers to use qubits, which can perform multiple operations simultaneously, making quantum computers faster than classical computers. They have the potential to revolutionize many fields, such as nature and science, by solving problems that are currently beyond the capabilities of classical computers. However, a sufficiently powerful quantum computer could undermine current encryption methods, posing challenges to data security. Quantum computers can be used to break many of the asymmetric encryption methods that we use today, such as RSA and elliptic curve Diffie-Hellman, considered to be hard problems that classical computers cannot solve in a feasible time. Today, our encryption and communication models rely on two math problems, discrete logarithm and factoring, which are extremely difficult to solve and considered as hard problems for classical computers. However, it was proven that there is a way to solve them by running Shor's algorithm on a capable quantum computer. Post-quantum, or quantum-safe algorithms, are thought to be secure against a cryptanalytic attack from a quantum computer, as they are based on different mathematical problems such as structured lattices and hash functions. Quantum computers are in their early stages and too small to crack public key cryptography today. A quantum computer capable of breaking encryption will likely require a large number of qubits that are substantially greater than today's quantum machines. While the use of quantum computers to break cryptography is still in the future, the threat is realized today. The effort to inventory and update all asymmetric cryptography will arguably be the most complex multi-year transition we have ever undertaken. There are increasing concerns related to attackers harvesting data now with a view to being able to decrypt it later when quantum computers are sufficiently mature. This is referred to as the harvest now, decrypt later style of attack. These mainly impact areas that need storage of long-term sensitive data, such as health records, or hardware and IoT devices, which will be deployed in the field for many years, and likely beyond the point where quantum computers can break their encryption. On Windows, our efforts have been concentrated on areas that offer the greatest leverage across this broad scope. To ease in this transition, we have been incorporating Post Quantum Cryptography algorithms into SymCrypt, the core open source cryptography library that powers our Windows and Linux operating systems. In addition, we have been updating our standard crypto API surface, CNG, or cryptography next generation. This includes the NIST standardized ML-KEM and ML-DSA algorithms for encryption and digital signatures, respectively. We have done so utilizing modern techniques, including implementations in Rust with formal verification to ensure the highest grade of quality and correctness. While these algorithms have been standardized, they are still new, and there is some risk that they could be broken, either with or without the presence of a sufficiently capable quantum computer. Thus, we are additionally providing support for the IETF-based hybrid composite algorithms, which easily combine post-quantum algorithms with their classical variants, such as ML-KEM combined with ECDHE. This allows safe integration of PQC algorithms into applications and protocols today without adding any additional risk. Above the crypto libraries, we are also pleased to bring in support for ML-DSA-based certificate and CMS APIs, including both certificate enrollment via Active Directory certificate services and certificate chain building through Crypt32. Lastly, our inbox implementation of TLS, S-channel, has been updated to support negotiation of hybrid-based key exchange groups, a critical piece needed to migrate TLS 1.3 connections to be quantum resistant from harvest now, decrypt later attacks. As global standards and regulations continue to mature in this ever-evolving space, we are committed to continuing to update our cryptography infrastructure to support customer needs. Now, let's look at our first demo, showcasing how you can use our CNG bcrypt API interface to perform ML-DSA signature and verification.
In this demo, we are going to showcase how you can leverage our CNG bcrypt API interface to generate new ML-DSA keys and sign messages. We have updated bcrypt generate key pair to support the ML-DSA cryptographic algorithms, which can be neatly passed into bcrypt sign hash and bcrypt verify signature with the bcrypt pad PQDSA signing context. This allows you to easily update your applications that are already using bcrypt for RSA or ECC today. Here you can see we first call our configurable application with ML-DSA 65, producing a signature of 3,309 bytes. Now let's compare with classic RSA 3K, producing a signature of 384 bytes. This highlights the size difference between ML-DSA and RSA.
For our second demo, we will now focus on composite ML-KEM for encapsulating data that can be shared with a peer via encrypt.
In this demo, we are going to showcase how you can leverage our new composite ML-KEM plus ECC parameter sets and new encrypt encapsulate and encrypt decapsulate APIs to encrypt and decrypt content via our CNG encrypt API surface. You start with our standard encrypt create persistent key API to generate new composite ML-KEM key pairs. You can then call encrypt export key to produce a public key to share with your peer. In this case, we chose ML-KEM 768 with ECDH P256, producing a public key of 1249 bytes. On the receiving end, the peer can import that key via encrypt import key. Once imported, that's when the peer can leverage our new encrypt encapsulate API to produce ciphertext and a shared secret. In this case, with ML-KEM 768 and ECDH P256, the ciphertext was 1,155 bytes. After sharing the ciphertext, the originating client can call our new encrypt decapsulate API to produce the same shared secret.
For our final demo, we will show an example of a TLS connection being updated to negotiate and communicate over hybrid key exchange groups.
In this final demo, we are going to showcase how our inbox TLS library S-channel has now been updated to support hybrid key exchange groups. Today, this requires updating policy on the device to configure negotiation of these new ML-KEM plus ECDH hybrids. After configuration, you can see with this Wireshark trace that by navigating to a peer which also supports hybrid key exchange, the appropriate quantum safe group was selected.
As a call to action, Post Quantum Cryptography is not just an upgrade. It is a fundamental shift to secure the next era of computing. Thus, you should start now, as transitioning takes time and early prep is critical. To start now, you should be planning Windows upgrades to the latest operating system, moving to TLS 1.3 where applicable, updating your applications for ML-KEM and ML-DSA either in pure or composite mode, and designing for crypto agility. Because algorithms will be changing in the future, the ability to migrate efficiently and safely is critical. Thank you for your time, and I am handing off to Jeffrey to conclude.
Now, let's bring it all together. Across Windows, we're making a set of commitments. Moving authentication off of legacy patterns, making code trust the default, and advancing cryptography so it stays ahead of future threats. Our shared responsibility is simple. Your software stays secure by default because the platform starts secure by default. That only works if we both do our part. For you, that means move off of legacy dependencies, sign everything you ship, design your apps for a world that's fundamentally different because of quantum computing and AI. When you take those steps, your apps run smoothly and your users stay protected. If you don't, friction shows up and your users feel it first. This is how we raise the bar together. We commit to delivering a stronger, more secure foundation. We ask you to meet us there so we can protect the customers we share. Because security only works when the whole ecosystem moves forward together.